Okay, so let's start.
Sure. Let me share my
You
screen.
want to share your screen again?
Yeah. Do you see it?
Yeah, I see it. Okay, so we're very happy to have Sanchit Chaturvedi from Stanford. He's a current PhD student of Jonathan Luke, and he's going to tell us about the vector field method for collisional kinetic models. So I'm very interested in this topic, and I was surprised and very happy to see all these papers being posted. And so I'm interested to hear more about the topic personally. So, okay, you're up.
Thanks a lot, Bob, for inviting and everybody for coming. Okay, so so I'm going to start with some background. I'm going to talk about like what the equations are, and then I'll move on from there. Okay, so kinetic collisional models. It's physically it governs the evolution of particle density over time, and the particles free stream till they experience collision, and when they interact with for the purposes of this talk with the Landau collisional kernel or the interaction kernel or the Boltzmann interaction kernel. The theorem we will have would be for the non-cutoff Boltzmann. Okay, so let me move on to Maxwellians and the global stability problem. Now, it can be checked with some work that the Maxwellians actually solved the Landau and the Boltzmann equations. And in the near Maxwellian case, dissipation due to collision is actually the main mechanism of stability. For Landau and the non-cutoff Boltzmann, the linear collisional operators behave like diffusion, and this has been proved in various works, starting with Guo for the Landau equation in a periodic box, and then Gressman strain 2010 for the non-cutoff Boltzmann equation, and finally Guo again for the Vlasov-Poisson Landau system. I'm missing a lot of works, but it seemed like these seem to be the most appropriate ones. Okay, so in the near vacuum regime, the things are a bit different. Collisions are rare, and since you're on whole space, the gas is also expected to disperse. To that end, there was a great paper by Illner and Schinbrod where they proved stability of vacuum for Boltzmann. For the cutoff Boltzmann via dispersion. So one could hope that actually the main mechanism for Landau and the non-cutoff is also dispersion and not dissipation due to collisions. So one would try to treat the collision terms perturbatively and hope that they degenerate in the long time limit. In contrast to cutoff Boltzmann case, the collisional terms apparently seem to have a derivative loss issue. We'll see that this does pose some issues, but we can actually get over it. And also, as a remark, all the results in the talk are in 3 spatial dimension. Okay. Also, if you have any questions, feel free to put it in the chat or interrupt me whenever. All right, so let's talk about dispersion from transport operator, because this is what we hope to use to prove stability of vacuum. Okay, so let's say that F solves the transport equation with initial data F0. Then using the method of characteristics, we can check that F at time t, position x, and velocity v is just the initial data at position x minus tv and velocity v. Now, for sufficiently localized data, this formula gives us the bounds for higher derivatives. You essentially just differentiate the form I gave for f0 x minus tv comma v, and you can see that the higher derivatives actually are bounded up to like 1 plus t to the power beta, where beta is the number of velocity derivatives we take, and we also have the corresponding L2 bound. Note that partial v worsens the t decay, and this can be seen by differentiating f0 x minus tv, whereas partial x does not affect that. So this will be useful for when we talk. I mean, this is a big part of the the issue that we have. Okay, so now let me talk about the velocity average, and this is exactly where we get the decay from. So one can check that the L infinity or the pointwise bound in X for the L1 norm in V actually decays like 1 plus t to the power minus 3. And if you take further velocity derivatives, then you have to give up like the number of that amount of time weights, depending on how many derivatives you take. The proof follows by using the change of variables x minus vt, and it's essentially just this change of variables. Okay, so there's another way to see this this dispersion, and that's through using space-time weights and the following functional inequalities. So if we want to bound the L1 norm for H, then you can bound it by x minus t plus 1v with four space-time weights multiplied by H and L infinity v, and you get like t to the power minus 3 as the decay. Whereas if you bound it in L2v, then you get t to the power minus 3 halves decay. All right, and this is also consistent with what you would get directly for the transport equations. Okay, any questions? No. Okay. All right, so then somehow this motivates. So let me motivate Kleinerman's commuting vector field method and why would it be helpful for us. So Kleinerman developed the commuting vector field method to study the asymptotic properties of wave equations without exactly understanding the linear operator. When I say exactly, it means somehow he didn't have to invert the operator. And the idea behind, or the philosophy behind this method is to find vector fields which have good properties when you commute with the equation. And the good depends on the context. So the upshot is that we don't have to invert the linear operator, and hence there's no need for exact formulas. So this is similar to Gou's energy method in that sense, because there you do an energy estimate. You can use the linear operator. You can get bounds to the linear operator, but you don't really need to invert it. Okay, so for the purposes of this talk, we will be using the vector fields partial x, partial v, and this weird y, which is t plus 1 partial x plus partial v. Now, the reasons to use partial x and partial v are somewhat clear, and they have been used for the past 20, 30 years. But the reason why we need y is a little subtle for the Landau case and has to do with the exact nonlinear structure for the Landau kernel. For the Boltzmann, it's clear and more in line with the philosophy, and has to do, and we needed to actually get this to understand dispersion for the linear operator, which is really just transport. I'll say more about this later. Okay, so now let me define what the Landau collisional operator is. So I define it to be, or it's defined as this aij hat, aij bar, and then second derivative of f in velocity minus c bar f, where a bar ij is aij convolved with f, and c bar is c convolved with f, and aij is the interaction matrix, and it's of this form, which is aij is it's delta ij minus zi zj over z squared times z power gamma plus 2. Right, and c is the second derivative of aij in velocity. And note, this is only this only works for gamma naught or bigger than -3, but for our purposes, this makes sense. So now the Landau equation essentially reads as transport, and there's this nice Laplacian-like term, and then you have minus CF. Okay, so now I'm going to say why there is essentially some time decay issue for the Landau operator, and why is there an obstruction to viewing it perturbatively? So now we do energy estimates for this equation, for the Landau equation, and take two partial x derivatives, then we always have a term which looks like partial to like second derivative in x of f, and then the two derivatives fall on aij bar, and you already have two derivatives in v for f. Now I use Cauchy-Schwarz to put second derivative for x in L2 L2, and the other second derivative in v in L2 L2, and I put aij with the two derivatives in L infinity x, L infinity v. Now, for the purposes of this talk, I'm going to ignore the velocity weight issues which exist and are somewhat tricky to deal with. But in any case, what one can see is that the second derivative of a in the L infinity norm is like second derivative of f in L infinity x and L1 v, and this can be seen since. So let me remind that aij is aij, which is a matrix convolved with f. Now this term has the velocity weights, but I'm going to ignore that, and then one can see that you're just integrating in v for f. Now the dispersive estimates that I talked about, so the dispersive estimates say that this term can be bounded by up to some norm. This can be bounded by 1 plus t to the power minus 3, and this term, the L2 term, can be bounded up to 1 plus t squared, because you have two velocity derivatives, and then you have to give up 1 plus t for each of them. And this is essentially coming from the transport. So when you combine these things, you get a decay of 1 plus t to the power minus 1, which is barely non-integrable. So this means that we need some new idea to be able to treat, actually treat these terms perturbatively. Any questions on this? Okay. All right. So to deal with this, Jonathan Luke came up with the null structure, which essentially says, oh, yeah, that's fair. You can just ask a question at the end. All right, so the decay estimates for transport are sharp because it's localized. So the way I view it is this is, let's say, the bulk. So this is x over t v. Then the decay estimates are sharp only when you're around this bulk, really. Otherwise, you have better estimates. And what this says is if x over t minus v is bigger than t to the power minus alpha for some alpha in 0, 1, you have better decay estimates. Now, there are three scenarios possible. So the first one is x over t is close to v, or the second one is x over t is close to v star. Or if neither of them is true, then or is not too close to v, x over t is not too close to v star. So x over t is further from v, x over t is far from v star, or v and v minus v star are actually close. Now, for the first two cases, bulk of the plasma is away from v of v star, so we can get decay from the transport, or the extra decay from the transport. For the last case, v minus v star is small, and 2 plus gamma is big. So what this means is we can somehow expect to get some sort of decay from this. So right. So since z is going to be small, where z is equals to v minus v star, we can hope to get some extra decay from this matrix. Okay. All right. So then then Jonathan proved the moderately, using this, he proved that for moderately soft potentials, that is gamma between -2 and 0. And if M is the number of derivatives you have for the initial data is large enough. Moreover, if you have, if the initial data is bounded by a Gaussian, which comes from here, and you have appropriate spatial decay to begin with, in this weighted Sobolev norm, you have the L2 norm and the L infinity norm is small for epsilon small enough. Then you have a global non-negative solution to Landau equation. And I forgot to mention that you also have to assume that the initial data is non-negative. Okay, so there's a remark that the number of derivatives you need approach infinity as you go to -2 or 0. So this is actually open. So this is important, and this has to do with the derivative loss issue in the pointwise bound. So Jonathan has to essentially propagate L infinity like the pointwise bounds, and this is why you approach the number of derivatives you need to approach infinity. Okay, so now I'm going to talk about my results for the hard potentials case for Landau and the soft potentials case for, or the moderately soft potentials case for Boltzmann. Okay, so the hard potential case is the gamma is between 0 and 1. The number of derivatives I need is at least 10. Then if the initial data is non-negative and you have, it's bounded by, this is bounded by an exponential in V, you have some spatial decay, which comes from here, and some extra polynomial velocity decay, depending on the kind of derivative you take. And it's small in the L2 norm, then you have a global non-negative solution to the Landau equation. Now, right, so somehow these, the way the weights are defined as somehow important, and I'll talk a little bit about why that is the case. And another thing to note is that I don't need any pointwise bound. I just need an energy bound, and so I just propagate energy estimates. Now, let me also mention my moderately soft potentials result for Boltzmann. So first, the Boltzmann collisional operator is given as there is this V minus V star power gamma, and then you have the theta singularity, which is theta to the power -1 minus 2s for s in 0, 1, not included, and you have the cancellation coming from post collision variables and then pre collision variables, and you average over all the angles on S2 and also integrate over all the pre collision velocities V star. Okay. So the theorem states that if S is between 0 and 1, so this covers all the singularity parameters, and gamma plus 2s is between 0 and 2, the number of derivatives at least 10, then for small enough epsilon and the initial data non-negative. Further, if we also have a spatial decay, this is a weird spatial decay, but it essentially just means that you have spatial decay, and you're bounded by a Gaussian, then in the L2 norm, then you have a global non-negative solution to Boltzmann equation. Okay, so let me give a few general comments on the proofs, my result and also Jonathan's result. So the space-time weights x minus t plus 1v, which essentially degenerates to x minus v for time 0, are used to exploit dispersion from the transport operator. And this is the function inequality I mentioned before. Now, in the near vacuum regime for Landau equation, vector field y is needed to exploit the null structure. And for the Boltzmann equation, y gives us further decay from dispersion of coming from the transport operator. Now, in contrast to Luke's work, where he propagates point-wise estimates via maximum principle, I actually essentially have to use a purely energy-based approach. And the reason is, for hard potentials, you have a moment loss issue in addition to the time decay issue. And also, for Boltzmann, you have a fractional smoothing operator as opposed to the second order operator you have for Landau. So proving any sort of point-wise estimate seems like a hard task. So I was too lazy to actually try to do it. So I just use L2 estimates. Okay, so some more remarks about the hard potentials case. As I mentioned, the time decay issue is coupled with the velocity moment loss issue. And one way to see this is that the Aij in this case, so without the hat, is or V minus V star is delta Ij minus V star I, V minus V star J over V minus V star squared. And then let's say gamma is 1. Then this would be V minus V star to the power 3. So essentially, then there's like, this is way worse than what you would have for the moderately soft potentials. So you also have a moment loss issue. Okay, but since we're only using energy estimates, then to avoid any sort of derivative loss issue, I have to make sure that there are at least 2 derivatives falling on Aij, because the form looks like this. So, and if I take any sort of derivative, I have to make sure that this term has the same amount of derivatives as the number I'm taking. So this I can do by an integration by parts. And so after noticing this, what I need to do is I need to use the null structure and also avoid the moment loss issue at the same time. And this is the reason why I have to design the weights in the way I did, to essentially exploit the null structure to the max and also not get the moment loss issue. I'm not going to say anything more about the weight issue because this is a little subtle. Okay. So let me move on to the time decay issue for the Boltzmann equation. Right. So now it's constructive to think of f or q fg as a fractional Laplacian of order s for s between 0 and 1. And in fact, thanks to Gressman's strain, we have this inequality, which says that if you pair h with qfg, then you have f in L infinity L1, g in L2 H2S. So you put 2 derivatives on g and no derivatives on h. And you also have these velocity weights, which right. Now, using dispersion from the transport operator, one can hope to get 1 plus t to the power minus 3 for the first one. And then this one grows like 1 plus t to the power 2s because you have 2 SV derivatives. And h is just bounded by 1. So combining everything like this, you get that you get a decay of 1 plus t to the power minus 3 plus 2s. Now, since s is less than 1, this is actually time integrable. And unlike for Landau equation, we don't need the null structure. But there's a problem. The problem is that proving this decay actually requires us to prove point-wise bound, and this is exactly what I'm trying to avoid, because Jonathan needed maximum principle to do it, and for Boltzmann, since it's not a second-order operator, it seems like a hard task. So if I use just L2 estimates, what the best decay I can hope for is t to the power minus 3 halves, and this is using the space-time weights. And the second inequality is just Sobolev, so that I put it in L2x. But now if I do this, then this the middle one still grows like 1 plus t power 2s, and this only decays like 1 plus t power minus 3/2. Now this, so the decay we get is 1 plus t power minus 3/2 plus 2s, and this is integrable only for s less than 1/4. So this is like, we are very far from being integrable for, let's say s equals to 1/2 even. So now this is where I need the vector field method, and essentially the point is I can get extra decay going from pointwise bound in X to L2 bound by using Y. So note, when I did for X, I just did Sobolev embedding directly, and I did not gain any time decay going from the first inequality to the second. But for this, what I do is and note that I need that I crucially use that I'm already doing a velocity average. So I'm doing an L2 average. Now the proof follows by fundamental theorem of calculus in X, and I use Y instead of partial X. So what I do is I write partial X as t plus 1 inverse Y minus partial V. Now, since we're integrating over V, the partial V terms drop out. Hence, we can combine, so then you actually get this estimate, the estimate that I mentioned here, at the cost of 3 Y derivatives. So what this means is that I can combine the decay coming from the space-time, which is the first inequality, and this is space-time weights. And the second inequality is the vector field trick. So in total, what I get is using just energy bounds or just L2 bounds, I can get 1 plus t to the minus 3 decay. And this is great because now all I need to do is prove an energy estimate, and I don't need to prove any sort of maximum principle. Okay, so what this tells us from combined with the first slide is that I can actually, that there is no time decay issue anymore. And this crucially uses that I can prove that I use both space-time weights and also the vector field Y. And further, this amounts to proving dispersion for the transport operator, and that's why I mentioned that this for Boltzmann it actually is it actually is a linear like a linear issue if I just want to use L2 estimates. Okay. So now I'll mention some other technical issues that I faced for Boltzmann, but I sweep under the rug. So the first one is the Gressman strain estimate I mentioned puts 2s derivatives on G, or you can distribute for S on G and S on H. But in any case, since dissipation term is not useful in the near vacuum regime, I need to treat the top and the penultimate orders differently, because otherwise I have a derivative loss issue. So the idea is to actually put derivatives on F instead of G and H for the top or the penultimate order. Now, further, the penultimate terms require a lot of massaging because we want the S to be greater than 1/2, or I need to cover all the singularity parameters. And for this, I need to use the integration by parts that was discovered by Henderson, Snells, and Tarfuglia in their local result for existence. And I also need to rely on the machinery of Imbert and Sylvester to essentially take care of the penultimate terms. Further, I also need to prove a lot of results to actually get the right amount of time decay. Okay, finally, the commutator terms due to space-time weights further pose further complications, and we actually need to employ another structure to treat them. But anyway, this does require a lot of work, but this is a minor point, and this is the null structure is only used when I do commutator estimates. Okay. All right, so I'm going to change gears and I'm going to move on to phase mixing now. So I'm going to move on to bounded domains instead of whole of R3. And more specifically, I will be on a torus. So okay, first of all, what is phase mixing and Landau damping? Now, in bounded domains, transport equations and also Vlasov-Poisson exhibit relaxation to an equilibrium via phase mixing. And one way to think about it is that the information escapes from lower to higher frequency modes as time evolves. So then you cannot. It's harder and harder to see this energy. Now, as a consequence is that the solution profile to transport of Vlasov-Poisson converges in the long time limit to a solution to a transport. And the smoother the initial profile, the faster is this convergence. Another consequence of phase mixing is that the mean removed density, which I define as, which is essentially you integrate f dv and you subtract the average over the whole torus, it converges to 0 in the limit. And this is referred to as Landau damping. And this is a pictorial depiction of phase mixing. Essentially, if you have a disturbance in your particle density at time 0, over time it just mixes, and so the disturbance homogenizes and goes away as time goes further and further. Okay. All right. So now let me mention the Muhovilani work for nonlinear Landau or nonlinear Vlasov-Poisson, and also mention the Landau damping. Okay, so consider the Vlasov-Poisson equation, which is transport plus the nonlinear interaction coming from the self-consistent electric field, and the E is defined to be the gradient of phi, where phi solves the Poisson's equation. Okay, this is the Poisson's equation. And I think I'm missing some constants, but whatever. Now, the Muhovilani work says that if I let f to be big F minus the Maxwellian e to power minus v squared, and there should not be this should not be there. Then for f initial, little f initial, which means that big F initial is close enough to the Maxwellian in an analytic norm, then we have exponentially fast convergence of big F to big F sharp, where big F sharp solves a transport equation. Further, the mean removed density, which I define as rho not equal to, which is again F integrated in V and with the mean removed, converges to 0 exponentially fast. So, okay, so this proves there are two things. The first is you have exponential fast convergence for the F itself, and also you have Landau damping, which is that the density converges to 0, the mean removed density converges to 0 exponentially fast. Okay, so now this the result that I mentioned for Muhovilani assumes analytic regularity, or for like later works have you can do it for Gevrey at least 1/3, but there is an obstruction to proving Landau damping for Sobolev data, and this is essentially due to interactions of nonlinear waves coming due to the nonlinearity. And for more information, you can see Bedrosian's paper, which is the nonlinear echoes in Landau damping with insufficient regularity. For more on this, as a picture to keep in mind is that periodically you have these waves that or this disturbances in the density that show up. So here, and then it shows up again, and then again, but they dampen over time. All right. So now what we have seen is that that for the nonlinear Vlasov-Poisson, you have some issue due to plasma echoes. Now, what I want to discuss is if I in the weakly collisional regime, as in if I put if I have some collisions, then you actually the plasma echoes go away, and you still have Landau damping. So what do I mean? So fix some nu small, and then consider the Vlasov-Poisson-Fokker-Planck for small enough perturbation of e to the power minus v squared. Okay, so what is the Vlasov-Poisson-Fokker-Planck? It's essentially Vlasov-Poisson coupled with, or you also have the Fokker-Planck equation with a nu in front of it. Then there are no echoes, and further we have enhanced dissipation. So what does this mean? And this is the content of Bedrosian's theorem, which he proved in 2017, which says that if little f is big F minus e to the power minus v squared, and we fix nu and epsilon small, and big M and big N large enough, then if you have the initial data is small in this weighted Sobolev norm, and is smaller than epsilon to our nu 1/3, then what we can prove is that the zeroth mode, the zeroth frequency mode, which is this dx, that's 0, is actually less than epsilon times nu 1/3. So this decays with e to the power minus delta nu t, and this is what you would expect because you have a nu in front of a Laplacian term, and so from heat equations we somehow know that this is what one should get. What is more surprising though is if you consider f not equal to, which is f minus f0, then you actually have a faster convergence, and this is e to the power minus delta nu 1/3 t. And also the mean removed density converges at the same rate as the mean removed f, where rho is defined to be integral in dv. So why does this happen? So now this is due to transport essentially. So what due to transport, the decay Vx is faster than what we expect for heat equation, which is e to the power minus nu t. So what really happens is the transport equation mixes things up and makes dissipation faster. Now, some comments on the proof. So Bedrosian relies heavily on the exact structure of the linear equation, which essentially means that he inverts the Laplacian from the Fokker-Planck, and so this is fine and all good for the Laplacian, but for the case for the linear Landau operator, this seems like a hard task, and I'll come back to it in a second. Now, a possible plan of action could be to employ the commuting vector field method, as this does not require us to understand the linear equation exactly. But what this requires us to do is to completely capture phase mixing due to the transport equation via vector field methods, and also understand the commuting properties of the vector fields with the nonlinearities from Vlasov-Poisson and also the Landau kernel. So we have to understand these three things. Now, I'm also going to compare Bedrosian's work with Guo's work on Vlasov-Poisson Landau, which came out in 2012. So, as I stated in the theorem, Bedrosian proves global stability of Maxwellians for Vlasov-Poisson Fokker-Planck and also enhances convergence to Maxwellian, assuming that the data is of size O1 or little o nu 1/3. Now, in contrast, if we just use Guo's Vlasov-Poisson Landau paper, we need to assume that the data is O nu, and this would give us the heat equation decay, which is e power minus nu t. And this is due to the collisionless terms, which we need to control by the dissipation terms. So let me go back a few slides to show what I'm saying. So the way Guo's proof would work is he would absorb these terms, the nonlinear term, by the dissipation term, but that would require us to have that E is of the same, somehow you have the decay from, or at least E is the same order as nu. Otherwise, you cannot hope to absorb it by the dissipation term. Okay. Right. Now, to prove an analog of Bedrosian result for Grasshopper-Poisson Landau equation, we need to capture both the enhanced dissipation and the Landau damping without inverting the linear operator. And we thus employ the vector field method to that end. And further, to capture enhanced dissipation, we have to employ hypocoercivity and also prove density and energy estimates in parallel. So so this is the main theorem. So let me state it now. So let's fix epsilon and nu small, just like Bedrosian did, and then if I let f to be, so let me define big F to be mu, which is e to the power minus v squared plus root mu of f, little f, and this is what this says. And assume that I have initially I have at least 20 derivatives in control in this weighted Sobolev norm. Oh, sorry, all of this should be f. This is little f. Sorry about that. So what this is, if the initial data is bounded by epsilon squared times nu 1/3, and okay, so epsilon is basically is of size O1. So this is independent of nu. Epsilon is little O1. Then if the number of y derivatives I take is less than m max, strictly less than m max, then the L2 norm of the derivatives with the right weight, and I also have to put this weird nu to the power beta over 3 weight, then I can say that this is bounded by epsilon times nu 1/3. I'll come back to this issue in a second. And if the number, if y is the only derivative you take, then what I can say is that y omega f in L2 is actually bounded by epsilon nu 1/6. So I have to lose a little bit at the top order, but okay. And the third thing I can say is that the mean removed density, which I define to be in this case now, which is this. Dx dv. This decay is like 1 plus t to the power m max, and you have and you also have the bound at epsilon to the power 3/2 nu 1/3. Okay, so this essentially is Landau damping. So this captures Landau damping, and the fourth one is an L2 in time estimate that I also have for essentially y alpha for the mean removed density, and that I can bound by epsilon power 3/2 times nu 1/3. Okay, so what this says is I have captured Landau damping, and in a weak sense, I have some sort of enhanced dissipation. I don't have the exponential conversion that Bedrosian has, but I'll mention that in a second. And sorry, I forgot to mention that this work is joined with Jonathan Luke and Thuan Nguyen. From Jonathan is at Stanford, and Thuan is at Penn State. Okay, so everything that I will talk about now is joined with them. Now, let me give a few comments on the theorem and the proof details. So, unlike for transport equations, which I will talk about in a second, the energy estimates are not enough to close estimates with the data of size O nu 1/3. We also need to prove optimal bounds for density to capture Landau damping. Okay. Now, the collisional term, as the theorem states, kicks in as at nu to the power minus 1/3 instead of nu minus 1. Then, so this is what we hope. Then, now recall that partial v costs us 1 plus t in transport equations because of this formula. Thus, a good dictionary to have in mind is that 1 plus t is essentially nu to the power minus 1/3. And this explains why I need the Newton power beta over 3 weight in my statement of the theorem. When I take beta derivatives in V, then I also have to compensate with the appropriate weight in nu. Okay, so this explains the weight. And now the velocity weights are chosen as Guo did for his proof. So this velocity weight of 5m max plus 10 minus 2 alpha minus 2 beta is exactly what Guo had to choose to close his estimates. And finally, the vector field Y is used to capture Landau damping coming from Landau operator. So I'm going to talk a little bit about that now. Now consider the transport equation on the torus, the 3 torus now. Now it can be easily checked that Y commutes with the transport, and thus Y omega F also satisfies equation number 5. Then just doing an easy energy estimate, we get that the L2 norm at time t for Y omega F is bounded by the initial L2 norm. Okay, so this is what we have. Now for the mean removed density, which I define as e to the power minus v squared over 2f with the mean removed, we can apply Poincare repeatedly because we are on torus to get partial x omega of the mean removed density, and then I multiply and divide by t plus 1 to the power minus omega. Now, since y applied to the mean removed density is just t plus 1 partial x rho, and y omega rho is bounded by y omega f in L2x and L2v. Sorry, this should be L2v. Then this is just by Cauchy-Schwarz. Cauchy-Schwarz. Then using these two things, I get using Poincare and this Cauchy-Schwarz estimate and the energy estimate, I get that rho at time t, the L2 norm is bounded by the initial data times you have the t plus 1 to the power minus omega decay. So essentially what all I'm saying is that y can be used to get the time decay that one would expect from Landau damping, at least in the Sobolev spaces. Okay, so now I'll talk a little bit about the density estimates that I have. Okay, the density estimates are an important ingredient for both Moho-Villani and Bedrosian. So I define mu to be e to the power minus v squared, sigma ij as aij convolved with mu. Aij is the same that I for the Landau kernel. Then the linearized Vlasov-Poisson-Landau near a Maxwellian for f such that big F is mu plus root mu f is this. I have dropped all the nonlinear terms. So this E term comes from when the derivative partial V hits on mu. Now the linear Landau kernel is defined to be this big mess, but one way to think about it is that the linear Landau kernel is essentially a second order divergence or divergence form operator plus zero, the lower order terms, which are of zero order. Now, for the Fokker-Planck operator, L is partial V, and Bedrosian can take Fourier transform in both X and V and apply Duhamel to get an equation for F tilde K and eta. But this requires inverting the Laplacian. Now, as I mentioned, in contrast to this, or also what we can see is taking the Fourier transform of and inverting the linear Landau operator, which is this big thing, is a challenging task to say the least. So what I do is we instead just take a Fourier transform in X, which commutes with L, and this is important because L is only it only depends on mu, which is X independent. Then you can write partial TF hat K plus, so this is the equation what we would get after taking the Fourier transform. And so now SK is the solution semi-group to this, and then let's just say that SK is the solution semi-group to this equation. The transport plus the second order operator I had. Then using Duhamel, we get F hat K is SK F initial plus plus the source term, and you force this, the source term. Then using this, I can write the density of equation for the density, which is by multiplying by root mu and then integrating in time. And although we don't know the exact form of SK, we can actually use energy estimates for linear Landau flow. And this is the essentially the idea that we need instead of inverting the operator. And what we do is we can get estimates for SK T minus tau for the source term, and then use the energy estimates that we prove in parallel for the Vlasov-Poisson-Landau problem to close the density estimates. Now, okay, I'm not going to say anything more about this, but we also need to use the appropriate kins of the usual Y that we were using for the estimates for the linear Landau flow. Okay, so I'm just going to quickly finish off by talking about hypercoercivity and some open problems. Now, to close our energy estimates, we use hypercoercivity, and essentially the idea is that transport operator speeds things up by speeds up the dissipation by mixing things up. And for concreteness, let me just consider the Fokker-Planck operator, which is partial T f plus vi partial x f is the delta v of f. Now, but differentiating in partial v, we get this extra minus partial xi term, which comes from the commutation of partial v and the transport operator. Now, if I consider the energy estimate for this cross term, partial VIF, partial XIF, then we get the coercive term, which is XIF squared, which is surprising to say the least. But and this is exactly due to because we commute partial V with the transport operator. Okay, to close the estimates though, we need to consider the energy estimate for the F in L2L2, partial XF in L2L2, the cross term we talked about, and partial VI F in L2L2 with appropriate constants A, B, C, and D. Now, if I replace the partial VF by new delta VF, then we have to choose A and B to be large enough constants independent of V, and C to be nu 1/3 and D to be nu 2/3. And one way to think about this is that in the weakly collisional regime, each partial VI must cost us nu 1/3, as we talked about, or cause 1 plus T growth. And this is the dictionary I was talking about, that 1 plus T essentially is like nu minus 1/3. Okay, so this tells us about the Fokker-Plancks, but since we have nonlinear terms and we also have, we need an energy estimate for using hypercoercivity for equations which are commuted with like higher derivatives as well. And the linear Landau operator replaces the Laplacian in our setting. Okay. So this is all I had to say about our proof. Now let me just mention some future directions and some open problems. Now, stability of vacuum problem is open for Vlasov-Poisson-Landau. And perhaps one way to do it is to use both Smilovic's idea with Jonathan Luke's null structure. Secondly, the stability of vacuum is open for Vlasov-Maxwell-Boltzmann system, even in the cutoff case, if I understand correctly. And finally, the stability of vacuum for Boltzmann is open for hard potentials. And some open problems for the weakly collisional regime. Now, the Vlasov-Poisson-Landau system that we in the weakly collisional regime we prove is for torus, and we need a lot of derivatives. But for general bounded domains, this is no good because we need like a low regularity result. Now, perhaps nu 1/3 is not the right scaling for low regularity data. And note that Go's method already gives us a lower regularity result for data of size O nu. So maybe there is a certain scaling in the middle, which would give us the right, the thing that we care about. Secondly, there is I mentioned that we did not prove any stretched exponential decay for density in the weakly collisional regime. But this should be true in the same way as the Go's proof for the Vlasov-Poisson-Landau and also strain Go for the Landau result. So one can expect to prove this result where you have boundedness from the initial data, and you also have decay, like a stretch exponential decay due to dissipation. And finally, in light of Mo-Villani's result, one can expect that for Gevrey data of at least 1/3, we can prove enhanced dissipation and Landau damping for size O1, for initial size of O1 instead of O nu 1/3. Okay, all right. Thank you for bearing with the talk. Thanks.
Thank you. Does anyone have any questions?
I'm sorry for going over time if I did.
No, that's okay. If you have questions, you can put them in the chat or you can unmute yourself. I have a couple of questions. So for the last set of results, which is that for Landau the similar assumptions to the earlier results, or is it for Landau Coulomb potential, or
sorry, I did not mention that. That's a fair question. It's for gamma equals, it's for the Coulomb potential.
Okay.
Yeah, let me go back and so it's for,
because you said Guo gets exponential decay. Guo gets exponential decay in the case when gamma is greater than or equal to -2.
I meant like stretched exponential.
Right? But okay, yeah, it was, well, you said, so when gamma equals -3, you get stretched exponential, but when gamma is when gamma is greater than or equal to -2, you get
exponential.
Exponential. And the stretched exponential was in the later paper that you mentioned at the end of your talk. But
right. I was talking about the Vlasov-Poisson Landau paper. I think he proves it directly, if I understand it right. The 2012 paper.
Yeah. Oh, yeah. But you don't get stretched. You get stretched exponential there, right?
Right. Yeah, that's right. Yeah.
Right. Okay. But here, this is for like gamma greater equal to -2, something like that.
So for the statement of so this one is for gamma equals to -3.
This one. Okay.
Yeah. This one. This statement. Okay. Sorry, I forgot to mention.
No, that's nice.
Yeah. So that's why I only expect stretched exponential. I don't even expect exponential.
But this is near equilibrium, so you linearize and you use a linear operator.
Right.
So you can prove results using the vector field method close to equilibrium, or is
yes.
Is this existence, or is this just
so essentially this is like a global existence result for all time, but okay. I mean, one can convert this and we hope to do it in another paper to actually get the exponential or the straight exponential decay.
Okay, then you would have to use weights, or I don't know.
Right.
I don't know how you would do it, but we use velocity. We use exponential weights in that case.
Right. I agree. And the point is why we can actually use vector field method is because the one way to think is that it's close to the transport equation because nu is small.
Okay.
So the y is only to understand the Landau damping, really.
Yeah. Yeah. And so for this one near Maxwellian, you can do gamma equals -3.
Yeah.
Is there any hope to do gamma close to -3 or for the near vacuum cases, or what do you think about that?
Yeah, I don't think so because the dispersion is not strong enough. I mean, somehow even for gamma equals to -2.
Okay.
Right. Even for gamma equals to -2, I don't think you can do it. It's exactly the amount of decay you have is 1 plus t.
Okay.
I don't know why I'm going back. There's no point. But essentially, it says even for gamma equals to -2, you don't have enough dispersion, or at least the way we do it. Maybe one can use the cancellation somehow in a better way instead of using the second order. The way it's written down as a second order operator, maybe one can just use the cancellation in a better way than perhaps, but I'm not sure.
Okay, that's fair. Thank you. I was curious about that.
Yeah.
Yeah, you can probably get this stretched if you can do all that other stuff. I'm sure you can get this stretched exponential decay.
Right. I think so too.
So did you just do gamma equals -3 here? You weren't worried
That's it.
about
Yeah.
gamma bigger than that, anything like that? You're just, okay.
Yeah, because I think presumably this equation is, or at least what physicists care about, I think, is only for -3.
Yeah, right. The Coulomb. The only case that they ever talked about in the physics literature is gamma equals -3.
Yeah.
Other gamma was invented in the mathematics literature. I have one more question. Is this does this do these kinds of methods require usually high regularity, like m greater than 20, or are there any
Yeah.
examples where you can do lower regularity for these in this kind of method?
I mean, from what I have seen, because they somewhat require high regularity, but maybe Jonathan perhaps knows of results where they can do low regularity too. I mean, okay, 20 is maybe more than, but it is at least 10. I mean, there's nothing I can do below 10,
Yeah,
so it's probably useless for what you want to do, or for bounded domains.
Yeah, I think so. Yeah, I agree with what. I think it's this sort of method somehow requires regularity. You can, okay, if you work very hard, maybe you can do, I don't know, 8, but to do, for instance, the kind of thing you did, I don't think. Yeah,
and infinity, yeah, I don't think so.
Okay.
And the reason is essentially because we're doing a hyperbolic type estimate, so you need some, at least for the EE term, you need some sort of decay to be able to integrate it out.
So because you have with the Landau damping, you usually require very, very high regularity, but for this
right
kind of method, this is actually low regularity compared to normal Landau damping results. But you also have the dissipation term, so that must
exactly, and that's what Bedrosian did for his Fokker-Planck, and this is somehow it makes sense. That's why we could do it for Plaza-Poisson Landau as well.
Okay. Well, thank you.
Yeah.
Those are all my questions for now.
Okay, thank you.
Does anyone else have questions? Okay, well, thanks again, Sanchit, for giving a nice talk.
Thank you.
I'm very impressed with these results, and I'm interested when your last paper comes out to read it. I wish we could take you out to dinner, but you're on a different coast.
I'll take you up on that offer some other time. It's okay.
Okay, yeah, some other time for sure.
Yeah.
You know, if you're ever in Philadelphia.